In an older existing precast concrete building with insulated interior piping and no effectively grounded structural steel, the question arises if the primary equipment grounding conductor, sized correctly per table 250.66, can serve as the grounding electrode conductor for the secondary X0 connection. The proposed grounding electrode conductor would connect to the service grounding bus bar, which is no smaller than the required grounding electrode conductor. This is not a code-compliant system according to the 2020 National Electrical Code. Section 250.32b2 states the grounding electrode conductor shall not be smaller than the primary equipment grounding conductor. Table 250.66 specifies how to size equipment grounding conductors. Section 250.50 outlines acceptable methods for installing equipment grounding conductors for a building or structure. Firstly, insulated. Secondly, bare. Thirdly, covered or sheathed. And fourthly, part insulated, bare, covered, or sheathed for part of its length and insulated for part. Section 250.112 mandates the grounding electrode conductor be connected to the grounding electrode system. If the primary equipment grounding conductor is insulated, as in this scenario, National Electrical Code Section 250.50 dictates that the equipment grounding conductor for a building or structure must be insulated. Therefore, the primary equipment grounding conductor cannot double as the grounding electrode conductor. A separate grounding electrode conductor is required to be installed and connected to the grounding electrode system. This separate grounding electrode conductor must be sized according to Table 250.66 and connected to the service grounding bus bar. To reiterate, the grounding electrode conductor must be separate from the equipment grounding conductor in this situation, and it must adhere to the sizing requirements outlined in Table 250.66. The purpose of the equipment grounding conductor is to provide a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices. The grounding electrode conductor, on the other hand, connects the electrical system to the earth, stabilizing voltage and providing a reference point. Combining these functions into a single conductor is not permitted in this scenario because it could compromise the effectiveness of both grounding systems. The sizing of the grounding electrode conductor is determined by the size of the service entrance conductors. Table 250.66 provides the minimum size requirements for grounding electrode conductors based on the size of the service conductors. The grounding electrode system typically consists of one or more grounding electrodes, such as a ground rod, ground plate, or metal underground water pipe. These electrodes are connected together to form a grounding system that provides a low resistance path to earth. The equipment grounding conductor, as mentioned earlier, is sized based on the rating of the overcurrent protective device protecting the circuit. The larger the overcurrent protective device, the larger the equipment grounding conductor must be. This ensures that the equipment grounding conductor can safely carry the fault current back to the source. In summary, the 2020 National Electrical Code clearly distinguishes between the functions and requirements of equipment grounding conductors and grounding electrode conductors. Combining these functions into a single conductor is not permitted in the specific scenario involving an older precast concrete building with insulated interior piping and no effectively grounded structural steel. A separate grounding electrode conductor must be installed and sized according to the code requirements to ensure the safety and proper functioning of the electrical system. The grounding electrode conductor ensures voltage stabilization and a reference to earth, while the equipment grounding conductor facilitates overcurrent protection. These are distinct roles that necessitate separate conductors in this installation. Ensure that the grounding electrode conductor is connected to an appropriate grounding electrode system as defined by the National Electrical Code. This system may involve ground rods, ground plates, or connections to a metallic water pipe system depending on the specific conditions at the installation site. Consult the National Electrical Code for detailed requirements on grounding electrode systems. Remember that proper grounding is essential for electrical safety, protecting people and equipment from electrical shock and fire hazards. Always adhere to the National Electrical Code requirements and consult with a qualified electrician when designing or installing electrical systems. This information is for educational purposes only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician for any electrical work. Furthermore, it's crucial to understand the specific requirements and interpretations of the local electrical codes and regulations, as they may vary from the National Electrical Code. Local authorities having jurisdiction, often referred to as HA, have the final say on code compliance and enforcement. Therefore, it's always recommended to consult with the local AHA to ensure that the electrical installation meets all applicable requirements. In addition to the code requirements discussed, it's important to consider the specific characteristics of the precast concrete building and its impact on the grounding system. The lack of effectively grounded structural steel can present challenges in establishing a low-impedance ground path. Therefore, careful attention must be paid to the design and installation of the grounding electrode system to ensure its effectiveness. The insulated interior piping also plays a role in the grounding system design. Since the piping is insulated, it cannot be relied upon to provide a ground path. Therefore, a dedicated grounding electrode conductor is essential to establish a connection to earth. It is important to note that the neutral conductor, also known as the grounded conductor, plays a critical role in the electrical system. While the grounding electrode conductor connects the electrical system to earth, the neutral conductor provides a return path for current under normal operating conditions. The neutral conductor is typically grounded at the service entrance, creating a single point of connection between the electrical system and earth. This single point grounding helps to prevent circulating currents and voltage differences that could create safety hazards. The size of the neutral conductor is determined by the unbalanced load on the system. The National Electrical Code provides guidelines for sizing the neutral conductor based on the expected load. It is important to ensure that the neutral conductor is properly sized to carry the anticipated current. In addition to the grounding and neutral conductors, the equipment grounding conductor plays a crucial role in protecting against electrical shock. The equipment grounding conductor provides a low impedance path for fault current to return to the source, tripping the overcurrent protective device and energizing the circuit. The equipment grounding conductor is connected to the metal enclosures of electrical equipment, such as appliances, machinery, and electrical panels. This ensures that if a fault occurs, the metal enclosure will be effectively grounded, preventing a dangerous voltage from developing. The equipment grounding conductor must be properly sized and installed to provide effective protection. The National Electrical Code provides detailed requirements for equipment grounding conductors, including sizing, installation methods, and connection requirements. It is important to adhere to these requirements to ensure the safety of the electrical system. In summary, the grounding system is a critical component of any electrical installation. It provides protection against electrical shock, fire hazards, and equipment damage. The grounding system consists of the grounding electrode conductor, the neutral conductor, and the equipment grounding conductor. Each of these conductors plays a distinct role in the overall grounding system, and it is important to ensure that they are properly sized and installed. Always consult with a qualified electrician to design and install a grounding system that meets the requirements of the National Electrical Code and local electrical codes. Proper grounding is essential for electrical safety and should never be overlooked. Remember that electrical codes and standards are constantly evolving, so it's crucial to stay up to date with the latest requirements. Regularly review the National Electrical Code and any applicable local codes to ensure that your electrical installations are compliant and safe. Moreover, consider attending continuing education courses or workshops to enhance your knowledge of electrical safety and best practices. These courses can provide valuable insights into the latest code changes and emerging technologies in the electrical industry. By staying informed and continuously improving your skills, you can contribute to a safer and more reliable electrical environment for everyone. Furthermore, it is important to understand the difference between grounded and ungrounded electrical systems. In a grounded system, one of the conductors, typically the neutral conductor, is intentionally connected to earth. This provides a reference point for voltage and helps to stabilize the system. In an ungrounded system, none of the conductors are intentionally connected to Earth. Ungrounded systems are sometimes used in industrial applications where a high degree of reliability is required. However, ungrounded systems can be more difficult to troubleshoot and may require special protective devices. The choice between a grounded and ungrounded system depends on the specific application and the requirements of the electrical system. Always consult with a qualified electrician to determine the best type of system for your needs. In addition to the above considerations, it is important to understand the concept of impedance in grounding systems. Impedance is the opposition to the flow of alternating current. A low impedance ground path is essential for effective grounding. A high impedance ground path can limit the flow of fault current, delaying the operation of overcurrent protective devices and increasing the risk of electrical shock. The impedance of a grounding system is affected by several factors, including the length and size of the grounding conductors, the type of grounding electrodes, and the soil conditions. It is important to carefully design and install the grounding system to minimize impedance and ensure effective grounding. Finally, remember that electrical safety is everyone's responsibility. Always be aware of the potential hazards associated with electricity and take precautions to protect yourself and others. Never work on electrical equipment unless you are qualified and authorized to do so. If you are unsure about any aspect of electrical safety, consult with a qualified electrician. By working together, we can create a safer electrical environment for everyone. Remember to regularly inspect your electrical system for any signs of damage or wear. Look for things like frayed wires, cracked insulation, and loose connections. If you find any problems, have them repaired immediately by a qualified electrician. Neglecting electrical repairs can lead to serious safety hazards. Also, be sure to test your ground fault circuit interrupters or GFCIs regularly. GFCIs are designed to protect against electrical shock by quickly interrupting the circuit when a ground fault is detected. Test your GFCIs monthly to ensure that they are functioning properly. If a GFCI fails to trip when tested, replace it immediately. In addition to the technical aspects of grounding, it's important to consider the human element. Electrical safety training is essential for anyone who works with or around electricity. Training should cover topics such as basic electrical theory, safe work practices, and the use of personal protective equipment. Make sure that all employees who work with electricity receive adequate training and that they understand the importance of following safety procedures. Furthermore, create a culture of safety in your workplace. Encourage employees to report any electrical hazards they identify and to speak up if they see someone working unsafely. By fostering a culture of safety, you can create a more proactive and preventative approach to electrical safety. In conclusion, electrical grounding is a complex and critical aspect of electrical safety. Understanding the code requirements, the technical principles, and the human element is essential for creating a safe and reliable electrical environment. By staying informed, following best practices, and fostering a culture of safety, we can minimize the risks associated with electricity and protect people and property from harm.